Hello and welcome to today's webinar with Volt DB titled The Fast Data Stack, an Architecture for Real-Time Decision Making. My name is Peter Viscuso. I'll be the moderator for today's event, but before we begin, I'd just like to review a few housekeeping items. This is a live presentation with On24, and although you can't see the other people on the line, we've got a large number of people. When we advance slides, sometimes there's a few second delay, so just be aware of that, and we'll try to monitor that. The presentation will last approximately 40 minutes, 45 minutes, and there'll be time for questions at the end. But I'd encourage you to put questions in as we go through the webinar. There's a Q&A window where you can type in your questions, and we'll collect those as we go through the webinar, and we'll address those at the end. Everyone asks, and I want you to know you will get a follow-up email from us with a copy of the slides and a link to the webinar, and we'll have an archived version of that available online. The phone lines are muted to cut down on background noise, but as I said, we welcome your questions. Please type them in as we go, and we'll handle them at the end. I would like to introduce our speaker today. It's Ryan Betts. Ryan is the CTO here at Volt DB. He's one of the initial developers of the Volt product, and he values his unique opportunity to collaborate with customers. I think Ryan spent, I don't know how many days on the road it was last year, but had on the order of 200 different customer meetings, and you might imagine with that level of interaction, he's got a great kind of perspective and experience in a wide range of areas, and he's a great font of knowledge. So as we go through, you have questions, please feel free to ask, and I'm confident Ryan will be able to address them. So with that, I'm going to turn it over to Ryan.
Thank you, Peter. And so today's webinar is entitled The Fast Data Stack, an Architecture for Real-Time Decision Making. So why use the concept of a stack here? We use software stacks basically to try to make solutions repeatable. We look for pieces that plug together well and that collectively solve a greater problem. And anywhere that we've seen really application acceleration occur, we've seen people be able to deploy lots and lots of applications of a certain type, whether they're web services applications or desktop applications. There's been some kind of a stack behind it. And when we think about big data and fast data, we certainly see an opportunity that crosses across marketplaces and verticals and geographies. So I think it's appropriate to try to assemble in our minds or on paper and eventually in practice a set of tools that work together to solve common fast data and common big data problems. Most big data projects have a workflow. First, they need to collect the information, the data that's going to be analyzed and explored. Once they've managed to collect that, sometimes as an ETL process from existing sources or as a continuous trickle stream ingest, there's an exploration process that needs to occur. That exploration is what we commonly think of as data science. And if that exploration is successful and some business hypothesis is confirmed, usually there's an analytical process that results. We take the results of that exploration and we try to summarize that result as some kind of an analytic outcome. And there are really two different types of analytic outcomes that come from big data analytics. The first are discoveries. These are big kind of one-off learnings, right? If you want to know, for example, if the planet is warming, you might look at a lot of data and see if you can make a big data discovery. Seasonal predictions, scientific results, long-term capacity planning. These are outcomes that usually need some kind of a human process to complete. This is knowledge, and to act on this knowledge requires us to create a business or a political effort or a planning effort. But there's a second type of outcome from analytic results, from the analysis of big data, and those are inputs to optimizations. We can find ways to take knowledge gained through the exploration and analytics of large data sets and apply those in real time to ongoing processes. Perhaps your big data discovery is how many roadways you'll need in a growing urban environment. but your real-time optimization might be real-time coordination of traffic lights to smooth the flow of traffic through that landscape. In both of these cases, you're relying upon the exploration and analytics of your large data set, but you're acting on it in two very different ways. A lot of times I talk to people who've managed to solve the collect and sometimes the explore portions of this cycle, but it's relatively rare still to talk to people that have smoothly solved all four aspects of this. The ability to collect large amounts of information, explore it, analyze it, and then to turn, especially in the real-time space, the outcomes of those optimizations into ongoing real-time interactions. Part of the reason I think that this is hard to solve is that solving the entire cycle requires a combination of technologies. The collect and explore technologies, I think, are naturally arrived in the marketplace first, and we're more familiar with them. They're more familiar to us. Some example technologies applicable to that part of the cycle are columnar OLAP warehouses like Vertica, right, or data warehouse systems like Teradata, the Hadoop ecosystem, and all of the different batch processing and now a kind of new SQL processing that can be done on it as an analytics application. And we know and recognize the uses of these different technologies to calculate large recommendation matrices, to do segmentation against a lot of market data so that we can segment our users into different categories. Oh, next slide. When it comes to the action phase, there's a set of requirements that are emerging, and this is really where I want to focus the talk on today. What's the stack to solve the fast part of this problem? The big problem is about petabytes. The fast part of the problem is often about very high throughput numbers. Another way to think of this is that the big corner is the volume and variety aspect of big data. The fast corner is the velocity aspect. When we want to be able to use the optimizations that we've discovered from our analytics phases in real time, whether that means real-time pricing in an electric grid or real-time personalization of a free-to-play game platform, we need to find a set of technologies that can interact against very high-speed event streams within a period of time, within a latency that allows us to insert that calculation or that optimization into the user experience. So we're talking about platforms that can process hundreds of thousands or even millions of events per second, often responding to each event in milliseconds. This is a very different technology type than the big data technology type. Another way to look at this is to look at it from the point of view of macro trends. Now, sensors, mobile, and SaaS infrastructures create vast streams of data. We know that these streams of data overwhelm our legacy databases in two facets. One, we know that they create more data by volume than those databases are designed to store and process economically and efficiently, and we know that the rate at which they create these incoming streams also exceeds the performance capacity of these legacy systems. There's a fundamental problem, though. To monetize these data feeds, we need to be able to write real-time per-event applications. So at MultiB, we believe that this application style is a lot like a traditional OLTP database application. I think a lot of times if you pictured what you might do to solve these problems if scale weren't an issue, how would you solve a personalization issue at small scale? It's quite likely that you would start from some kind of a database architecture. So MultiB provides a database architecture that allows you to maintain that solution pattern, but at scales that are orders of magnitude beyond what a traditional database can accomplish. When you start to look at how fast data and big data are combined into an architecture, kind of lay out another point of view what the big and fast pieces look like together, you can see that you start to create a collection of tools, and they interoperate. Data is flowing from the fast side to the big side, and analytic results are flowing from the big side back into the fast side so that they can be used for real-time decision-making processes. I want to dig into the fast data stack, and I want to look at some of the different requirements that are outlined here. The fast data portion of this architecture has to be capable of ingesting data at the rate of the incoming stream. It has to be capable of performing real-time analytics that need immediate responses. It needs to be able to generate application responses back to the source or alerting and thresholding alarms off to adjunct processes that are watching these big data or fast data analytics for real-time action. And then finally, in many cases, there's a real-time ETL or real-time transformation component. We're doing sessionization, enrichment, denormalization, and filtering of these incoming data feeds so that we have an archivable kind of forever data stream that we can store immutably into the big data side of this application. When you put all of this together, you see that there are really a set of requirements that a fast data stack has to meet. And to try to communicate that, we've placed these into something that looks like a hierarchy or a stack. That's the title of this webinar, the Fast Data Stack. At the top, you have applications and message queues, data sources. The stack has to be capable of ingesting these. And then there are both analytical and decision or transactional processes that occur after that ingestion. And then connections to the big data side to accommodate export and the construction of data pipelines from the fast to the big side. On the analytics side, there are really two key requirements. One is the requirement to calculate analytics, to actually calculate and produce the counters, aggregations, time series, and statistics that are needed. And then secondly, to serve those results, to make those results interactive and queryable by applications that require them. There's also a need to be able to drive real-time decisions, to be able to enforce per-event policies or to evaluate a set of campaigns against discrete incoming events, and in many cases to drive back real-time synchronous responses to those incoming events in order to communicate personalization data or to communicate a path to optimization back to the event source. So when we look at the fast data stack in its entirety, we see ingest, analytics, decisions, and this export big data integration all as key components. How do we think about the type of technology that might address these different needs? There's really three different ways that I've thought of to look at this problem, and I'm sure there's many more. I'd love to hear other people's thoughts and questions around this. When I look at this problem space, I really see three different avenues that we can use to examine it. We can think about it first from a data-centric point of view. What are the types of data that need to be managed by this fast data platform or fast data stack? Secondly, we can think about it from a communication point of view. How is data flowing through the fast data stack and the big data stack together? What are the common data flow patterns? And finally, we can think about it from a processing point of view. What are the analytics and transactions and queries that are necessary to solve a large number or a large variety of fast data problems? So I'm going to walk through these in turn. Let's start with looking at it from a data point of view. A lot of times when people look at these problems, they're initially overwhelmed by the velocity of the incoming event stream. And they become focused, very severely focused, on just the incoming events as the sole piece of data that needs to be managed. And that's a mistake. When you do this, what you'll find is that you'll end up with an architecture that solves the ingestion problem, but it often doesn't solve or offer the capabilities of real-time analytics and real-time decisions. There's a big difference between a system that can simply record a series of events and a stack that can combine the capabilities of fast and big to support real-time applications. If you want to support real-time applications, you need to consider not just the incoming event stream, but also several other different types of data. You have real-time analytic results that need to be served. The Lambda architecture, for example, addresses this explicitly as the serving layer. There's often event metadata. For example, if you're collecting readings from a smart grid, you'll have a little bit of data for each meter, the concentrator that it's assigned to, the version of software it might be running, perhaps whether it's a meter under your monitoring control or under a competitor's. And in all of these cases, you'll have to use that metadata to correctly process the incoming stream of events. There are OLAP analytics used in real-time decision-making. For example, if your big data platform is generating real-time personalization and recommendation data that you would like to combine with real-time session state or perhaps real-time inventory state in order to make an optimal choice, then you'll have to combine that OLAP analytic output, the recommendation matrix or the personalization parameters, with that real-time session state. And managing that OLAP analytical data is another component of data that needs to be considered when you're assembling a fast data solution. And then finally, there are the outcomes of the fast data stack that need to be managed. There are both responses or side effects, alerts or alarms or synchronous responses back to an application that need to be created. And then there's the outgoing event stream. This is what I referred to previously as the archive stream, the set of filtered, transformed, and enriched data that you would like to capture into your historical archive so that you can add it to your big data collection. Three of these different pieces of data are stateful. They need to be managed across more than the life cycle of a single event. The analytic outputs obviously span events. The metadata or lookup tables that you're using for data enrichment, filtering, or sessionization often will live beyond any single event. This is a piece of data that spans multiple event processing points. And in many cases, these real-time streams involve some implicit session, and these sessions need to be assembled. For example, someone was telling me recently about a use case for detecting fraud for prepaid phones. And commonly, someone can buy a prepaid phone. You see a series of events, a set of suspicious calls, and the phone never receives a phone call, and various VoIP options are used. Then it's highly likely to indicate international calling fraud. To identify that, you really need to be able to assemble a session, the records or the events that happened to that phone over the first 30 or 60 minutes of its lifetime in order to make a detection of fraud that you could then act upon. So that's an example of session state that spans multiple events. Secondly, we can look at this from the point of view of communication. How does data flow through fast applications? There are three data flows. We'll look at them one by one. The first is an analytics data flow. In this case, there's an event stream or some incoming log stream that's hitting the fast data platform or stack, and the fast data stack is producing a real-time summary of that state. It's calculating real-time key performance indicators. It's looking for alerts or alarms or activities that might indicate fraud. Sometimes it's just doing simple counting to drive dashboards for your customers so that they have transparency into the real-time state of their platform. In this case, the data is often arriving at the fast data platform where it's simply being summarized, and a set of analytic results are made available for query either by a user or a dashboard or another application. A second data flow is a second data flow is a request-response pattern. This is really what the most traditional database application pattern looks like. We're all very familiar with applications that make a request to a database and that receive a response that enables the application to continue on. This also happens in fast data applications. Mobile authorization, real-time campaign spending metrics. Does a campaign have dollars still associated with it that allow it to serve an advertisement? Real-time quota enforcement against very large APIs, micro-personalization, recommendation serving, the list goes on. All of these are request-response patterns where an application is driving hundreds of thousands of events per second that a real-time database needs to be able to respond to. And finally, there are pipeline data flows. These are places where data is flowing through the fast data stack, and the fast data capabilities are being used to enrich, filter, denormalize, correlate, sessionize these incoming data feeds so that they can be persisted. In many complex applications, you'll actually see a combination of these data flows. Often there's an analytics component so that you'll have transparency into a real-time environment. In some cases, there'll be alerts, alarms, or some kind of response back to an application that causes some action or behavior, going back to the collect, explore, analyze, and act cycle. And equally often, there'll be some ETL process or some transformation process that's integrated into that. So I don't mean to imply that a fast data application is only one of these three things. On the contrary, it's very important to consider that your application may have all three of these different data flow patterns. And when you consider the requirements of a stack to solve that, you should consider which of these patterns might be present in your application space. Finally, we can look at the requirements for a fast data stack from the point of view of processing. What are the calculations and analytics that are necessary? There are three types of processing that I commonly see when I speak to customers and to other big data practitioners, and I describe them here as continuous query, transactional event evaluation, and transformation. These are really the verbs that we're applying to the incoming event. Continuous query, for example, might be a streaming aggregation or a materialized view in MultiB speak. A transactional event evaluation is policy enforcement or campaign enforcement. And transformation is the filtering process, the rewriting of data. There was recently a couple of blog posts that were describing SAMSA as an immutable system, and they were discussing immutability of data sources and whether a database should look at data as something immutable or something mutable. I have somewhat strong feelings about this, and I think it's the wrong question. What we commonly see is that when data is new, it's kind of emerging from this primordial soup. It mutates very, very quickly. Anyone who's tried to write complex applications in front of an append-only OLAP system will understand that the capability or the missing capability of updating data is often a pain point. What we see when you combine fast data and big data applications together is that the fast data stack provides a place where data can be mutated very rapidly when it is new until it forms a complete session or the analytic summary of a time period is complete or the transactional response for a fraud detection can be fully kind of upserted and responded to. At that point, often the data is frozen. So I think that when I look at databases and I ask myself whether they should treat data as mutable or immutable, I kind of come to the conclusion that the answer is both. When data is new, you need some way to mutate it and to make it fully formed. Once it's frozen, often that process might take seconds, sometimes it might take hours, but once that record is complete, then you would like to archive it, along with all of the other telemetry that you use to kind of freeze it into some kind of an OLAP system for historical processing. From that point on, it may remain immutable. If you put all of these different pieces together back into the stack, you can start to see that there's really a number of different requirements that have to be met. The stack has to be able to manage stateful data. It has to be able to flow data through in a pipeline fashion. It also needs to be able to run transactions to produce responses back to applications that require real-time per-event decisions. If you try to assemble this stack from the Apache assemblage, you'll see that you need to choose a large number of tools and combine them in order to meet this requirement. You'll often have something, for example, like Storm for aggregation attached to a serving layer for query. And even then, you haven't managed to create an application stack that can do real-time decisions. Often you're still doing not even per-event processing, but micro-batch processing. And so you'll introduce other technologies like Cassandra or HBase to try to find some transactional component. Having these things separate, the analytics from the decision becomes a pain point, and you begin to write messaging protocols between these different platforms so that they can exchange data. Or you start to do things like run Redis caches on each of your Storm nodes so that you have somewhere to maintain persistent state. We think that the reason that this is so hard to do with these combination of technologies is because they're fundamentally the wrong architecture. They're the wrong technologies to solve this problem. At MultiB, we think that this is namely a transaction processing problem. If you consider all of the different aspects of the problem, the requirement to maintain state, the requirement to make the results of analytics queryable and interactive, and the requirement to be able to respond transactionally on a per-event basis, all of these things are the traditional capabilities of a transactional processing system. The difference is that Volt allows these things to occur at a rate and at a throughput the traditional disk-based systems can't. When we look at the other technology choices that are available, they really fall into three buckets. The OLTP model, which MultiB advocates, a streaming model which answers some of the aggregation problems and some of the ingest problems, but that doesn't suffice for real-time per-event responses and that doesn't include an integrated query layer, and then a columnar analytics problem that allows you to maintain real-time analytics in some cases, but that doesn't usually offer any kind of per-event capability. another way to look at this is as the streaming technology stack. If you look at just the streaming technology stack, you'll see that there are a number of different streaming platforms out there. And if you compare the capabilities of this stack to the full set of capabilities of the fast data stack, you'll see that they don't cover the capabilities or the requirements to allow data to be queryable, and they don't cover the requirement for real-time decisions. And if you look at the capabilities of an OLAP-focused stack, or the stack based upon a columnar analytics, you'll see that you'll have an analytics capability. You can maintain counters and aggregates. You can ingest data and summarize it, but that you don't have the capability of producing real-time decisions, and that you don't have a system that supports the fast mutation or sessionization of data or the filtering of data because of the missing capabilities of fast update. So when we put all of this together, we get what we think is the correct fast data stack. Sometimes we talk about this as a streaming data pipeline. You have applications, producers of logs and sensor data, message queues, all producing fast incoming streams of events. And you have a platform capable of the four primary functions of the fast data stack: ingest, analytics, decisions, and export. A platform that can respond on a per-event basis, that can enforce per-event policy, and that can still produce real-time streaming aggregation for real-time analytics, and then pass transformed data downstream to an OLAP system for archive. And that also allows that archival system to push back analytic results into the real-time space so that you can use your historical analytics to further optimize real-time interaction. Another way to say this is that streaming apps are really database applications when your database is fast enough. So thank you very much for listening through this. I would be more than happy to answer any questions. And having reached the end of the prepared presentation, let me apologize for my raspy voice. I have a bit of a cold today, and I hope that it didn't translate too poorly over the phone. So thank you.
Thank you, Ryan. And we do have a couple of questions. As attendees can see on the webinar window, if you do want to try VoltDB, we certainly encourage you to do that. We think it's one of the best ways to experience the unique features and capabilities of Volt. You can download and use the enterprise version, or there's an open source version available on GitHub. So, one of the questions that came up is, you talked a lot about Volt, but never said explicitly what is Volt. And there's a lot of different components and approaches that people use for streaming. What is Volt? Why is it well suited to streaming?
That's a good question. So VoltDB is an in-memory scale-out transactional database designed to process transactions at a very high rate of speed. If you look at SQL systems, they've been largely specialized to different purposes. There are columnar analytics systems that are specialized towards analytics against historical data. VoltDB is a database that's been specialized towards high-throughput transaction processing. Volt provides a scale-out system, a lot like a NoSQL-style system. However, it provides rich ACID SQL transactional capabilities as part of that, and includes integrations. We call them VoltDB export, so that you can connect VoltDB in a pipeline to a downstream system. So, for example, you can receive an event in VoltDB. You can run a transaction against it using the full capabilities of an ACID SQL database. And then you can write data as a result of that transaction to a VoltDB export table, where it enters a persistent queuing mechanism and will be pushed downstream to a set of connected endpoints. They could be Hadoop, HDFS, a columnar system like Vertica, a queuing system like Kafka or Rabbit. So we use VoltDB to solve all the different aspects of the fast data stack. We use VoltDB to write very fast request-response applications that require high throughput authorization. We use VoltDB to do real-time sessionization and transformation of data with archival over a VoltDB export to a downstream system. And we use VoltDB for real-time analytics, real-time summary of very fast-changing data, offering a full SQL interface to query those analytics as they're produced by the platform.
Great. Thanks, Ryan. It was on the streaming data pipeline diagram, but in small print. One of the questions is, do you mean to say that Volt can replace the Kafka and other messaging streaming systems? So, it was hard to see kind of where Volt fit in with that and be helpful to clarify that.
A good question. In many cases, we think that VoltDB is very complementary to Kafka. Kafka is often used as a place to buffer incoming events so that they can be processed by multiple downstream systems. In fact, VoltDB ships connectors to Kafka so that you can load data directly from Kafka to Volt in a real-time continuous process. Where we think that VoltDB, or where we look at VoltDB as a replacement or an alternative to some of the Apache technologies, it's really the combination of the CEP, Storm, or streaming Spark systems, along with the serving layer that they require, along with often the persistent caches that they need to fully realize the fast data requirements.
Great, thanks. A couple of questions on export. I'm going to read they're related. Looks like you can export data back to data warehouses, and can you export back to relational databases? So can you ingest from IBM mainframe databases like these?
Yeah, we provide some connectors, JDBC connectors to traditional relational databases, kind of in the same way that we have connectors to Kafka to feed data to VoltDB. We have connectors to JDBC systems. I don't think we have a connector directly to ESAM. We produce export output through a pluggable connector framework. So we have a simple API that can be implemented in order to connect our export data to a downstream system, and we provide existing connectors for Hadoop, Kafka, RabbitMQ, relational systems over JDBC, and in some cases to relational systems like Vertica over some of their more performant interfaces. We also provide the capability to feed data from those systems back into VoltDB. For example, we have a VoltDB Hadoop output format that you can use. You can essentially invoke the VoltDB bulk loader by running a Hadoop query, rather through Hive or Pig or Spark. You can one example application that we ship and make available is using Hadoop and Vertica as alternatives to one another to produce a k-means clustering report, and then we export that report back to VoltDB using either the Hadoop output format integration for VoltDB or our Vertica UDX integration for VoltDB. And that allows VoltDB to do real-time event classification against that cluster data. So there's an example of how we're using OLAP analytic results in VoltDB in real time. You can be receiving data to VoltDB on a per-event basis, and you can use the clustering data that you generated or the clustering analytics that you generated from your OLAP platform or your Hadoop platform to inform real-time scoring and real-time decisions.
Right. Kind of a related question on Hadoop. I think you might have answered it, but maybe it needs clarification. Do you mean to say that we need to have Hadoop running as a hand-in-hand approach to solve real-time problems? Hadoop's not a requirement. Right? No,
it's certainly not a requirement. I would say that of the many VoltDB deployments, somewhere between 65 and 70% of them are actually deployed in combination with some kind of a platform. And what that platform is really varies pretty broadly, and we're quite agnostic to it. Our intention is to provide the real-time capabilities that are required. People run VoltDB in front of everything from TokyoMX to Vertica to Teradata to Hadoop, with those systems providing often an historical archival capability, VoltDB's in-memory technology being used for the real-time application component. There are certainly applications where VoltDB is deployed standalone. VoltDB is a standalone SQL system, and it doesn't have any dependency on an OLAP system to function. But what we find is when people are solving data at scale problems and actually looking at the entire cycle from collect, explore, analyze, and act, they often end up assembling a set of technologies together into a platform. And that's why I talk about VoltDB as part of a platform in many instances.
Great. Another Hadoop question. Can you join data from Hadoop Hive tables in Vault queries?
No, at present we don't support joins from Vault to Hive. That's actually an interesting question, but the reason is also, I think, a good one for why we don't support this. VoltDB is usually running applications that are running hundreds of thousands or tens of thousands of transactions per second. And reaching out across a network to a Hive table to query that Hive table and extract data at that velocity isn't feasible. It wouldn't work. That's really the value that Volt is providing in the platform, or when you're looking at these tools in combination. Volt's providing the capability of running complex transactional processing on a per-event basis at almost unlimited throughput. People have built Volt clusters that process 6 to 10 million transactions per second, and those were like 16 to 20 node clusters. We're talking very small cluster footprint for very vast throughput. So instead, what we do is take more of a caching approach. We take analytic results from those OLAP or analytics platforms, and we cache them into VoltDB, and we use them for some short period of time, at least at human scale, 5 to 10 minutes perhaps, and then we'll refresh them. It's not feasible to touch those analytic results in those analytic systems at hundreds of thousands of times per second.
Great, thank you. We get this question a lot. Volt is in memory. How does it handle disaster recovery, backup, et cetera?
Yeah, VoltDB is an in-memory system. All of the data that Volt manages is memory resident in DRAM. However, it's fully durable to disk. It provides a built-in high availability and fault tolerance model through replication within a cluster, and then across geographic areas provides an asynchronous replication for disaster recovery. So VoltDB has the capability of snapshotting itself or producing a checkpoint, and then between checkpoints it produces a write-ahead log or a journal. And it can do all of that without degrading its throughput performance. The way that VoltDB is architected and organized allows that.
Yeah, I think you answered it with the checkpointing remark. How do you do transaction rollback? Is it like regular SQL databases?
Yeah, in VoltDB, the transaction model is based upon one interaction with the database is exactly one transaction. So you can represent a transaction as a single SQL statement in an auto-commit mode, as a set of SQL statements written into a DDL file, or as a combination of SQL and Java written in a Java stored procedure. All of those things are a unit of a transaction. In VoltDB, most commonly, people will structure their transactions as Java stored procedures using SQL for data access and data manipulation and Java for business logic. One way to look at this is if you're familiar with other scale-out platforms like, for example, Storm. Storm provides you a way of writing a small amount of Java, plugging that into a platform, and then the platform provides you some set of capabilities. It manages scale-out and to some extent fault tolerance. In VoltDB, users typically write a little bit of Java representing their business logic and transactional logic and plug that into our database, and we scale that out and partition the incoming event stream across that, and while running those transactions, provide the full capabilities of an ACID database, so all of the state and query capability that you would expect in a traditional row store. VoltDB is fully atomic on a per-transaction basis, and it maintains an in-memory log to manage undo state. So if a transaction rolls back or is not committed by a user, then that rolls back, and there's appropriate undo state maintained in memory within VoltDB.
Great. Thank you. And how would you compare Volt to SAP HANA, another at least partially in-memory offering?
Yeah, SAP HANA is largely an analytics platform. It organizes data primarily in a columnar format and provides a set of kind of delta merge capabilities that give it some amount of capability to update existing data. VoltDB is very much a transactional row store, first and foremost, and is designed to run a very large number of high-throughput transactions, each of which touches a relatively small percentage of the database. HANA is kind of the inverse of that.
Okay. And you talked about streaming data applications, fast data applications. Are there any sample applications available? Yeah,
in the VoltDB kit, if you download VoltDB, there are 4, I believe, applications there showing some common capabilities of the system, using it for real-time windowing, real-time cardinality estimation using hyperloglog, an application that demonstrates VoltDB making per-event decisions in a very simple way called Voter. And if you go to github.com/VoltDB, you'll see both the open source offering for VoltDB as well as a set of applications that have been collected there that are further demonstrations of the database. And if you have a specific sample application that you're curious about, feel free to reach out to us. We've obviously written many applications. Not all of them have been made publicly available, but we often have a sample that you can get started with.
Okay. Here's a specific question. How might we get ongoing updates to a relational database system into Vault as a stream of changes? Is that a CEP question?
No. So there's really two ways to do that. You can write You can write an application that's processing the change data log out of that and forward that to VoltDB, for example, as a plugin or as an extension to some kind of a replication system. Or alternately, you can write those changes to a table within your relational database and use the VoltDB JDBC connector to read them. So typically to solve that problem would require extending some kind of a replication platform to be able to speak to Volt.
Great. Okay, I think that covers it. Thank you, Ryan. Thanks to our attendees. We appreciate you participating. If you have any additional questions that we didn't see or we didn't get to, we'll follow up with you directly. You'll get an email from us, as I said, within about a day with a link to the recording and the slides. Thank you, Ryan.
All right. Thank you, Peter.
Thanks for everyone to attending. So long.